How are you, Professor?
Hey, how's it going, Chad? I got your email. I hadn't got a chance to get back up with you regarding that yet.
It's all right. Yeah, I was waiting till the meeting to just ask you in person to
Gotcha.
help me out with it because, yeah, you saw what the email was specifically about, right?
Yes.
Yeah, I just don't know whether or not but was there something else I have to do for that?
Now I will check. I'm going to be checking over everybody's grades probably in the next, probably before the weekend, and I'll give you a standing of where each of you are actually. And I'm being really pretty lenient, so I wouldn't worry too much about it right now. But definitely, like I said, I should have something to you before the weekend goes.
Okay, and you saw, like, I mean, aside from the question with the points, you also saw my issue I was having with the test.
Yes.
Yeah, I mean, I've been trying to get into it day after day. Like, I just thought like maybe it was just a daily issue or so. So I just thought, maybe it was just a bad day. Tried to do it, and like yesterday, I tried getting into it again. It's
It
just
still didn't do it, yeah.
yeah,
I'll open it up for a little longer and see what we can find out. And yeah, I'm not sure what's going on regarding that. That one was a little confusing to me.
yeah. I'll be back. I just gotta get my charger.
Okay. All right, I think I got everybody's name on the roll now. Might help if I chose the right class. Okay, looks like everybody's up. All right, does anybody have any questions before we get started? I actually got something I'm planning on talking to you guys about this time as opposed to just taking questions and letting you run. So does anyone have anything they want to ask me about? I know Chad did, and I got to get back up with him as well. I guess. All right. Well, I'll tell you what I'm going to do. I'm going to start off. We're going into chapter 28. I made a video. It hasn't been posted yet, but I did post another video. Actually, there's two more videos for chapter 27. One of them's posted. The other one's not. The post for chapter 28's not up yet either. So I thought I'd go over this part. This is sort of the only thing that's sort of confusing. So I thought I'd go over this, which is the Law of Biot-Savart. And then I want to go over the Amperes Law, and that should help you get started on any homework you want to do for chapter 28. But I thought it'd be better to have a real life scenario where you guys can actually ask me questions as we're going along. So just feel free to unmute yourself and get my attention as I go on a roll if you don't understand something. But I'm going to try to write bigly, like that word bigly, and clearly so that y'all can see it. Let me go ahead and switch to the doc cam. Hopefully y'all be able to see. So there's that. You try to get it in focus. Okay, can y'all see this? It looks digitized on my side, so it's kind of crappy.
It's fine, except for like the R squared and the R cubed look a little.
Yeah, they're kind of small. I figured that might be the case. I'll explain that part, so that won't bother it quite so much, but we'll see. Let's see if I can. Spotlight video. Okay, so I'm gonna put this here so I can see that. All right, yeah, see, and it's still got a little blur to it. That makes it, there you go. All right, so what we have is the Law of Biot-Savart, and this is the most complicated thing from this chapter. The other parts are sort of like Gauss's law, so it's not that complicated. But this is the Law of Biot-Savart. It basically says that a small infinitesimal amount of magnetic field, dB, can be calculated by taking mu zero, that's a constant, is 4 pi times 10 to the negative 7th. Let me write it up here. And the units of that are actually Tesla times meters per amps. Okay, 4 pi times 10 to the -7th, and the units are Tesla meters per amp. So you take mu0, you multiply it by the current. So this is a wire, say, in space, carrying a current I. You multiply mu0 times I, divide that by 4 pi, and then you take the integral of dl. dl is a little tangent vector to the wire at a point along the wire, and the dl has to actually point in the direction the current's going. I couldn't draw dl pointing that way. It has to point that way because that's the direction the current's going. Okay. Then check this out. You have to take a cross product of that with a r hat vector, and the r vector is a vector that points from the source of the magnetic field, which is the little segment of wire dl, to the point that you wish to know the magnetic field. So this is a point P. That's where you're trying to calculate the magnetic field. So this is the general diagram that has to go along with this. Now notice it's a 1/r² law, just like Coulomb's law. So it's dl cross r hat over r squared. But like we learned before, r hats are a pain to calculate because this isn't an I hat, a j hat, or a k hat usually. So you have to make the vector, find the magnitude, divide the magnitude or the vector by the magnitude, and then you have the r hat. So why not just make this r cubed in the bottom and just say r on top? That's what I did here. So that's the way we're going to use it. mu0 I over 4 pi times the integral of dl cross r over r cubed. So that is a mouthful. It's the nastiest equation that you get in a second semester calculus-based physics. It really is ugly. And this first problem that I'm going to work for you is probably the worst case scenario. All the other ones are a little more straightforward. So what I'm going to do is I'm going to imagine a wire. So this is a wire. It's actually laying on the paper. It's pointing in the positive y direction. The current's actually flowing, conventional currents flowing in the positive y direction. The x direction is to the right. And without any loss of generality, I'm going to say the point is actually on the x-axis. Because notice, if this is the wire, then any point in space, I could align the x-axis from the center to that point, and I'd get the same answer. So I'm not choosing some highly specific thing when I'm put the point on the x-axis. Let me back out of this a second. I think I just heard someone trying to log in. Maybe not. Okay, looks like I guess everybody's here. All right, so make sure. Manage participants. Is it okay? So I didn't miss anybody. All right, so this again is no loss of generality. We're assuming the distance from the center of the wire to the point in question is a distance r. That's not a variable. It's just an r. When we work it all out, it's not necessarily related to this r. It just is the perpendicular distance from the center of the wire to the point in question. In other words, the minimum distance. So I'm going to show you how you can apply this beast to this problem and calculate the magnetic field around a current carrying wire, a distance r away from it. So first thing I'm going to do is I'm going to choose a dl. Remember, dl is a infinitesimally long unit or vector, not unit vector, but an infinitesimally long vector that points parallel to the current. So what I'm going to do is I'm going to say this is dl right here. It's basically just a unit vector, just an infinitesimal vector dl pointing in the positive y direction. So I'm going to say dl is in fact equal to dy in length. That's what makes it infinitesimal, but it points in the j hat direction. So I write that. So dl is just dy j hat. Now remember, the r vector has to point from the source of the magnetic field to the point in question. So that means my r vector goes from here to here. I think you can see that has a y component that is, if I call this y because it's along the y-axis, this distance right here is y. So that means this component of the vector r is in fact y units long and points in the negative j hat direction. So I'm going to say r vector is negative y j hat. And it also points to the right along the positive x-axis, a distance r. So I'm going to say that's plus r I hat. Does everybody follow what I did there? All right, no questions? So now I've got the DL and I've got the R. I think you could probably guess how I'm going to find the magnitude. Since they're mutually perpendicular, I'm just going to square this, add them together, take the square root, and I'm golden. So I'm going to now compute the actual magnetic field. And it's going to seem kind of hairy for a bit, but it's actually pretty straightforward. You get lucky, the integral's quite simple. So B, which is equal to the integral of dB, is going to be equal to mu 0 I over 4 pi, remember the current being carried is I, times the integral of dl, which is dy j hat, but that dl is crossed with r, and r is negative y j hat plus r I hat. Oops, I wrote I hat here and I meant a j hat, sorry. Okay. And then the r cubed, remember, because I've got a whole vector here instead of a unit vector. Now I've got to take this magnitude and cube it. So I'm going to take y squared plus r squared. And I'll take the square root of that to get the magnitude. But then I got to cube it because it's the cube of the magnitude. So I'll write 3/2. Now that seems kind of hairy. But let me show you how this vector is going to, cross product's going to play out. One of the neat things about vectors, cross products and dot products, is they're what we call linear operations. So if I want to take the cross product dy j hat crossed with negative y j hat plus r I hat, then all I have to do is take the cross product with the first part. And that literally means just take this magnitude and this magnitude, multiply them by each other. So I get negative y dy j hat cross j hat. Dang, I wrote I again. J hat cross j hat. So see, I took all the magnitudes, the negative y and the dy, and pulled it out in front. And the only cross product that's really going on is j hat crossed with j hat. Well, you know, A cross B is equal to the magnitude of A, and I'm taking the magnitude now, times the magnitude of B times the sine of the angle between them. So these magnitudes are 1 and 1, and then the angle between them is 0, and the sine of 0 is 0. So this is going to give me, in fact, the 0 vector. So nothing comes out of that first part. Now the second term, I got to take the dy j hat and cross it with r I hat. So I'm going to say plus, I'm going to pull the dy out in front and the r out in front. So r dy, and now I'm going to do j hat cross with I hat. Okay. Now in this case, it's 1 times 1, and the angle between them is in fact 90 degrees. So sine of 90 gives you plus or minus 1, depending on whether it's 90 or 270, blah, blah, blah. But the big thing is here, cross product still obeys the right-hand rule. So if I actually look at this xy down here, if I take j hat and cross it with I hat, then I see my thumb, notice I'm using my right hand, my thumb is pointing down into the page, which a right-handed coordinate system has z pointing out of the page, so this must be in the negative k hat direction. So I know this vector right here is negative k hat. Any questions on that part? All right, so that is really the nastiest part of all this. The rest of it comes pretty easily. So now I can go ahead and get rid of all this junk. I'm going to say B is equal to mu 0 I. I'm going to pull out the negative k hat because k's, I hats, and j hats are always constant vectors. That's not true for spherical and polar coordinates and stuff like that. Those vectors actually have to be integrated, but the I hat, j hat, and k hat can always be pulled out. So I got the 4 pi out in front here. All that's left from this old nasty cross product is that negative k hat and then r dy. So I'm going to say integral of r dy over y squared plus r squared to the 3/2 power. Okay. Now I'm going to have to integrate that from y equals negative infinity to infinity. That's how I take into account that the wire is infinitely long. Now this integral is not that pretty, but I like to use my trig substitutions. So what I'm going to do is I'm going to let y equal r tangent theta. The reason why is if y is equal to r tangent theta, I'll get r squared tangent theta squared plus r squared. So I can pull that r squared out in front. R squared to the 3/2 power is going to give me an r cubed in the bottom. And that's going to cancel out, of course, with the r up here. But I'm left with 1 plus tangent squared, which is a trig identity that I happen to know is equal to secant squared. And that might seem problematic until you realize that dy, when I make this trig substitution, dy is equal to r secant squared theta d theta, because the derivative of tangent is equal to secant squared theta. So now I'm going to have another r up top. That'll make r squared up top and an r cubed at the bottom. So I'll end up just getting a single r in the bottom. So now I can plug all this back into my integral and say that b is equal to negative mu 0 I k hat over 4 pi integral r squared secant squared theta d theta over r squared. I'm going to go ahead and factor out the r squared. 1 plus tangent squared theta. Now I should have put the tangent squared over here, but I flipped it. But I think y'all can figure out what's going on with that. That's not a big deal. And all that's raised to the 3/2 power. So 1 plus tangent squared is, of course, secant squared theta, which raised to the 3/2 power gives me secant cubed. So I have a secant squared under a secant cubed. That'll be secant in the bottom is all that remains, but secant in the bottom is the same thing as cosine in the top. Similarly, this r squared, when I raise it to 3/2 power, the 2 is multiplied by 3/2, and I just get r to the third under r to the first, so I end up just getting an r to the single power. So let me go back and write this with all that new information. So now I'm going to say b is equal to negative mu 0 I, put my k hat right here, over 4 pi r. Notice I had an r squared, an r cubed. The r squared canceled out with 2 of the 3 and left an r in the bottom. And that's equal to the integral of cosine theta d theta, because again, this is secant squared down here. Once I raise secant squared to the 3/2 power, that becomes secant cubed. Secant squared under secant cubed, over secant cubed gives me secant in the bottom, but secant in the bottom is the same thing as sine in the top. So I've now made everything a lot simpler. The only problem is my range of integration. Well, if you look at the diagram, when I said y equals r tangent theta, then tangent theta would be y over r, and tangent's opposite over adjacent. So you see, oh, this must in fact be the angle theta. So my range of integration can now be changed to theta equals negative pi over 2 to pi over 2. In other words, 90-degree angle is going to allow it to point to infinity, and then another 90-degree angle is going to allow it to point to positive infinity. Well, the good news is cosine is an even function, like if you make a graph of cosine, it looks like this. But then if you look at the other side, it looks identical. So integration over a symmetric range is the same thing as taking the integral from 0 to one end of that range, but multiplying the integral by 2. So I can change this to theta equals 0 to pi over 2 and put a 2 in there to account for it. And that'll make it a little easier as well. So I don't have to do, you know, 2 limits of integration and all that stuff. So carrying on, this 2 is going to cancel out one of those 2's. I get negative mu 0 I over 2 pi r, which you guys might recall. That looks very familiar to a formula you've used. Now the integral of cosine is actually sine because the derivative of sine is cosine. So this gives me sine of theta evaluated from 0 to pi over 2, which equals negative mu 0 I over 2 pi r in the k hat direction, with the negative, of course, times the sine of pi over 2 is 1 minus the sine of 0 is 0. So I end up getting exactly what we expect. B is equal to negative mu 0 I over 2 pi r. Ooh, r's in the bottom, sorry about that. Times k hat. Now, remember that negative tells us something. So if we're talking about a wire, let's take this wire right here. Remember, it's pointing this way. Let me pick it up. I'm going to pretend like it's this blue pin. I'm going to pick it up, and I'm picking up the axis with me. So now the x-axis is over here. The y-axis is coming up towards us. And then, of course, the negative k direction is that direction. So you see when I'm right here, the magnetic field points that way. So that if you imagine a line connecting the center of the wire to the point of application, then you have to follow that line and then take a hard left to get the direction of the magnetic field. So if I do that again over here, it's going to go this way. It's going to point that way right here. And it's going to point this way over on this side, and it's going to point this way over on this side. So in fact, looking from above, if we have a current carrying wire with the current coming out, then I go over to here, the magnetic field is going to point that way. And if this distance from here to here is r, then this is going to have a magnitude mu 0 I over 2 pi r. Similarly, when I go over here, it's going to point this way. When I go over here, it'll point this way. When I go over here, when I go over here, it'll point this way. And in fact, we get yet another right-hand rule. If you grab the wire with your right hand, with your thumb pointing in the direction of the current, so up out of the page, then your fingers curl around in the direction the magnetic field goes. So the magnetic field, as seen from above here, goes in a counterclockwise direction around it. So that is the result for a fairly long, in other words, if you're closer than at least a factor of 10, closer to the wire than the wire is long, then you can assume this is a fairly accurate result. And the result is that the magnetic field will be equal to mu 0 times I over 2 pi times r, and will wrap around in concentric circles around the wire according to the right-hand rule as I just discussed. Does that make sense? All right, so that's sort of the nasty of the nasties. That's you know, and you can see it's kind of just like the problem we did on the first day of class when the first day when we got into Coulomb's law, where I showed you that integral and calculated the magnetic or the electric field a distance away from an infinitely long line of charge. I even had to use the same trigonometric substitution. So I think by now you've probably gotten pretty used to that. The good news is the vast majority of the problems will be way simpler than that. So you'll use the law of Biot-Savart to do things like, let's find the magnetic field. Let's imagine now, we're going to imagine the center of a circle is right here. We're going to come some distance r away and make a quarter circle. and we'll imagine the current is flowing that way in that quarter circle. And then that current's going to take a right along the line connecting it to the center of the circle. And then it's going to take a right again, like so. And then it's going to take a right again, like so. So what we get, ignore this little line, what we get is a sort of a little loop, if you will, but it's shaped like two parts of a circle. So we'll call this one radius R, and we'll call this one radius big R. And we'll say basically this distance right here is A, so that you can say, oh, okay, well, obviously big R is little r plus A, but we won't need that. So now let's say we want to calculate the magnetic field at the center of this. This looks horrible. It looks like the worst possible scenario, especially when you think about using the law of Biot-Savart, but it's really not that bad. So the law of Biot-Savart tells us that B is equal to mu 0 I over 4 pi times the integral of dl cross r over r cubed. Okay? So let's handle it one piece at a time. Let's first think about this ugly part right here. My dl might be this. So this is dl, and I'll put a b for it, meaning the bottom. So this dl on the bottom, if I called this the x-axis and I assume this was the y-axis, then the dl would actually equal negative dx in the I hat direction, the negative, making sure that you're going the right way, okay? But check this out, the r vector for the bottom is right here, and they're parallel. And when you take the cross product of two parallel vectors, you get 0. So I can already tell that the contribution to the magnetic field at this point right here is 0 due to that guy. Similarly, for this one, we have a dl, and I'm going to call this dl left. So this dl left is going to be equal to dy in the j hat direction. And of course, the RL right here is actually anti-parallel to it. So again, the cross product is going to be 0. So I get no contribution from there. Now, once I jump to this part, things get a little bit more interesting. I've got, in this case, DL, and I'll call it capital I for inner. DL is going to be, let's call it R, the little r, times d theta, where basically d theta is that little angle right there. I know I wrote that too small for you to see, but I said it. So the angle right in that little wedge, which makes the distance of dl, is d theta. And it's going to point in that vector that we talked about before, that's the theta hat direction. Okay, so that helps us get that. And of course, for that inner part, the r vector is going to be equal to, now in this case, you're going to go basically this way and this way. It's actually going to be in the negative r hat direction. So I'm going to say negative r times r hat. And when I do the cross products, we can work with that, and it shouldn't be too much of a problem. So when I do the outer, it's going to be sort of the opposite. The outer is going to be a dl is equal to r d theta, but it's going to be in the negative theta hat direction. And the r is going to be instead negative big R, r hat. So let's do the inner part. Anybody have any questions so far? I've drawn a lot of stuff there and nobody has asked me any questions. That kind of worries me that I might just be blowing you guys away. Okay, well, let's do the inner part. I'm going to say BI for just the B field due to the I part, due to the inner part, is equal to mu 0 I over 4 pi times the integral of dl, which we decided dl is r d theta, theta hat, and I'm going to cross that with the r inner, which is negative r hat. So theta hat points this way, negative r hat points this way. So you see theta hat cross r hat points straight up. So this result should give me just r squared d theta pointing in the k hat direction. Okay, because I had an r there and I had an r here. That's where the r squared came from. The d theta was there. And I just did theta hat cross negative r hat and got positive k hat. So all of that will be over r cubed, because remember I took the whole vector, so I have to use a cube there. So what was looking really bad and scary and all that stuff all of a sudden becomes mu 0 I r squared over 4 pi r cubed integral d theta k hat direction, and we're going to integrate it from theta equals 0 to pi over 2. And in fact, you could just call it theta if you wanted to. For any concentric circle at radius r, you'd get a result that's related to theta as opposed to, you know, pi over 2. So what I'll say is the inner result is mu 0 I over 4 pi r times pi over 2 k hat. So that's the inner. If you wanted a more generic result for any angle theta, so instead of just saying theta equals 2 pi, the angle is actually going to be, say, some angle theta. If you wanted that for a radius r, then b would just equal mu 0 I over 4 pi r times theta in radians. And of course, you'll have to choose a vector direction. So I'll just call it v for vector direction, even though I didn't specify it. So don't confuse this with velocity or anything. I just mean a specific direction. You're going to have to use like a right-hand rule and figure out what's the right direction. Obviously, the current's going this way. If I grab that wire this way with my finger pointing in it, you'd expect the magnetic field to come out, which is the k hat direction on here. So that's part of the result. The other part of the result is the outer one. So the outer loop gives me BO, didn't mean that, but that's funny, mu 0 I over 4 pi integral, and again, this is going to be theta equals, in this case, we could say theta is going to start at pi over 2 and go to 0 if you wanted, or you could just treat it as that. It doesn't really matter too much, but in this case, the DL for the outer is negative r d theta theta hat, and that's going to cross with the r vector, which is again negative r hat, but this is a big R this time. And all that will just be over r. Oh, excuse me, that's supposed to be a big R here, not a small r. That's the same for this here. That's supposed to be a big R. Everybody see that? That's supposed to be a big R. So that's a big R as well. Now, again, I can just do theta hat, negative theta hat cross negative r hat, or you could just think about this wire. The wire is carrying a current this way, so I expect this one to actually force the magnetic field in the downward direction. So I'm going to ultimately get r squared over r cubed again, so that'd just be 1 over r. So I get mu 0 I over 4 pi r for this case. Now this time it's pointing into the page, which is the actual negative k hat direction. So I'll put a negative here and a k hat there, and I got to integrate d theta from theta equals, again, you got to be careful here. You just want to make sure you don't screw up your signs. So if I was actually treating this as the theta variable for polar coordinates, I'd have to go from pi over 2 to 0. Or if I just treat it as if I'm just going to get the magnitude that I want, then I can still do 0 to pi over 2, and that'll work out just fine. And notice that's completely consistent with using this. So just using this formula, I know the result should be mu 0 I over 4 pi big R times pi over 2. So really, I shouldn't use it this way unless I be very careful to change the sign afterwards. So I'm just going to say theta equals 0 to pi over 2. So I get negative mu 0 I over 4 pi R k hat, or excuse me, pi over 2 k hat. So the net result is, in fact, mu 0 I, B total, mu 0 I over 4 pi R factors out of everything, as does k hat. And then I'm going to get, or excuse me, not the R doesn't factor out everything, excuse me. So mu 0 I over 4 pi factors out of everything. And what I got left from this one is pi over 2 times 1 over R. And what I got from this one is negative pi over 2 times 1 over R. So in fact, I could have, in fact, canceled out that pi over 2 as well, or factored it out. And I ultimately get mu 0 I over, now pi over 2 divided by 4 pi becomes mu 0 I over 8. Okay, because the pi cancels out and the 2 multiplied by the 4 gives you 8, times 1 over R minus 1 over big R, all in the k hat direction. So that's the total magnetic field at the center of this weird shape here. So that's the two things I wanted to make sure you guys could go off with tonight. I'm not going to, make you do any more right now, but I'm certainly open to questions. Does anybody have any questions? You good, Chad?
Yes.
Go ahead.
I'd say I'm good.
Okay. Janie, anybody? Of course, this will be posted in video form in a few minutes, so you can look back at it, on your own time, and you can pause it many times. That might help you a little bit. But those are the two sort of tricky types of problems you're going to do with this. Amperes law is actually a real easy way of avoiding this, but just like Gauss's law, if you're using it to find a magnetic field, you can only do so when you have very specific symmetries. So it's not that Amperes law is Ampere's sometimes helpful hint. It's still a law. It's just a matter of, if you're using it to calculate the magnetic field, you're not going to be able to do it unless you have those symmetries. So I think Janie's gone.
One question, would you be able to post a picture of the actual pieces of paper? Because I was following along, but there were some things that was kind of hard to make out.
Hard to make out? I will. Problem is, some of them have been since destroyed.
Oh, yeah, no worries.
Yeah, and not only that, I tried doing it at one time, but the document cam, when it takes a picture, it does it with way worse resolution, and they don't come out very good.
Okay, then no worries, though. I can just follow.
I'll see what I can do, but like I said, if it doesn't, it's because I couldn't successfully find it, or I couldn't successfully get a decent picture of it.
Oh, gotcha.
Okay.
And then for the next test, do we have a set date for it yet?
Yeah, so I'm thinking I'll probably open it up on Monday. I need to be looking at the calendar when I'm doing this. Let me check my calendar real quick. I'm thinking I will open it up Monday. That'll be the 4th, and I'll just leave it open until probably midnight on Sunday the 10th. That way I can cover as much material as I can get covered. Y'all can use that over and over. And I might even randomize it a little bit so that you can take maybe 2 or 3 attempts. And I'll take only your highest.
Okay.
Okay. So yeah, expect it to come out on the 4th. and expect it to be due at 11:59 on 5/10.
Okay. And then for us picking our grading scale, do you
Mhm.
recommend, like, will you tell us, like, what our.
Yeah, I'll give you a really good estimate of what your grade is before you have to make that choice. But there is that formal process that you have to go through. I think you have to do my eval and then choose through that. They give you a route when you do that you can actually go
Yeah.
online and change. So make sure you do that formally, but I will let you know. I think that has to be in on the,
I think it's the 10th.
yeah, I think it is the 10th. So I'll let you know before the 10th. I was telling Chad earlier, I'm going to go through the grades, and I should probably have y'all with a pretty good idea what your grade will be going into the final. I should have that probably done by Friday.
Gotcha.
Okay. And that goes for anybody that has my lab, for instance. If you have my lab, or if you have anybody else's, if you get it done by Friday, chances are you'll know what your complete course grade is by Monday, other than the final and the last test.
So for physics, is it like chemistry where the lab grade is included in your physics grade?
Yes. Yeah. You get one grade for both of them, but 20% of the points comes from the actual lab grade, which if you didn't get me, you probably got, did you get Mr. Ippolito, or did some of y'all get Mr. Brune?
I got Bruin, and I think we're about done with our labs.
Yeah, I think you're supposed to be. I will go through those grades when they give them to me. And I've been a little more lenient on my students in my lab, so I might be adjusting your grades, but only in a positive way. So I won't make them lower by any stretch of imagination if you're in another
Gotcha.
teacher class, but I will probably make them higher, if not leave them exactly the same. Okay?
Got it.
Anything else? All right, well, actually, let me show you one more thing before I let you go, and then we'll call it quits. Just look at this document cam again real quick. There's this neat law called called Amperes Law. And basically it starts off with a magnetic flux, an idea about magnetic flux and stuff like that. But it turns out that the closed integral of B dot dl, okay, is equal to mu 0 times the enclosed current. So this is sort of like, cancel spell video. This is sort of like Gauss's law, where we had the closed integral of B dot dA is equal to 1 over epsilon 0 times Q enclosed. But this time we have a current enclosed, and instead of having a surface integral, we actually have a line integral. So let me show you real quickly how that works. So I'm going to do that same problem we just did with the law of Biot-Savart. Let's imagine a really long current carrying wire. The current's going that way. What I'm going to choose is what we call an Amperian loop. So it's called Amperes Law. So I'm going to create an Amperian loop. And the deal is you try to choose a loop and it's got to be a closed circle. That's why the closed circle is on the integral. But you choose a closed circle that's everywhere parallel to the magnetic field or exactly perpendicular. Because if it's parallel, B dot dl just becomes B times dl. And if it is parallel, chances are you're also going to have B being a constant. So you'll just get B out in front of an integral of dl. So you're just multiplying B times the length. That's the trick. If you can find that type of symmetry, then you can easily solve for it. So what I'm going to do is pretend like there's an Amperian loop centered on the wire going around in that counterclockwise way as seen from above. Looks like, okay, cool. I was just making sure no way. So if I choose that loop like that, then the left-hand side of Amperes law becomes the closed integral of B dot dl is just equal to the integral of B acting in the theta hat direction, dotted with dl which is in fact also acting in the theta hat direction, but you might even say DL is in fact equal to R d theta times theta hat. So because of that, this B is a constant everywhere on it. That's why I chose B to be some constant times theta hat. I end up getting B times the integral of R d theta, which just gives me the length of the loop around the circle. So you just get B times 2 pi R. Well, the current enclosed inside of that loop is consistent with the right-hand rule, so I call it a positive current. If it was the other way, I'd have to call it negative. So the right-hand side just becomes mu 0 times the I that's coming out of it. So now I've got B times 2 pi R is equal to mu 0 times I, or guess what? Exactly the same result that we got from the law of Biot-Savart. B equals mu 0 I over 2 pi R. And if I wanted directions, I could say B is acting in the, say, theta hat direction, which I'm pretending like theta goes around that way. So that's it. That's Ampere's law. You're going to repeatedly do that kind of application, just choosing your Amperian loop. So everywhere it's parallel to the magnetic field. So that you get B dotted with DL just becomes B times the integral of DL, or B times the length. Or it'll literally be perpendicular, in which case you get a 0. So that's all I'll say about that. You folks are free to go. Feel free to ask me any questions. I'll wait for the last of you to leave, and we'll call this meeting over. Have a good one, folks.